Hi, everyone. The Genomics Education Alliance, or GEA, aims to support genomics course-based undergrad research experiences, or CURES, by curating existing resources, developing new resources, and sharing them. We focus on tools, curricula, faculty training materials and strategies, and assessment materials for implementing CURES. The Faculty Training Committee of the GEA is specifically in charge of sizing up faculty training needs from a survey and curating and or developing the most requested resources and strategies for implementing CURES. So I'm just going to zoom in. So we developed a survey and sent it to over 20,000 faculty, including NSF-PIs, network faculty from the Genomics Education Partnership, GCAT-SEEK, etc. We sent the faculty to department chairs from hundreds of minority-serving institutions and community colleges. The most highly requested resources for implementing CURES in the future were standalone lessons, online tutorials and courses, workshops, and CURES in a box. By CURE in a box, we refer to comprehensive resources provided for CURE, including the research question, data, tools, curriculum, and assessment resources. And these are often highly helpful for people not interested in generating their own data. Minority serving institution faculty did not differ strongly from non-MSIs with respect to required resources, but they did rank highest in the category of not implemented yet, but interested in running a CURE. Community college faculty were most unaware of what CURES were and were most concerned with the ability to meet external standards. Both MSI and community college faculty were concerned about insufficient student background. Okay, regarding the requested resources, the GEA Student Learning Committee is developing lessons and courses to support CURES. The faculty training group is curating and displaying faculty development workshops on our website for easy sorting by level. And I can quickly flip over. Okay, so here's our our website, and if you go to workshops, you'll see a list of the faculty training workshops that we have selected that we thought would be good based on feedback we got from the survey. And and you can go to this link for faculty training workshops and pick through the workshops we have displayed by their tags. So if you wanted beginner workshops, looks like the GEP faculty training workshop is coming up, and let's see, another one is coming up as well. Okay, and you probably would be interested in online workshops. So online training is another tab we have. And a series of those is also displayed. Okay. So the next thing I wanted to do was talk about our efforts to develop genomics templates. So we focused on two types of CURE templates, one involving RNA-seq and one genome annotation. And the posters focused on RNA-seq, but we have a companion document, Word document, that you can look at for genome annotation, eukaryotic gene annotation. Okay, the initial goal of the RNA-seq template outlined here is to frame important considerations, possibilities, and solutions for introductory students interested in an RNA-seq-based cure, and based on web analysis of existing data, and then guide users towards implementation. Thousands of complete RNA-seq data sets are publicly available at the GEO database and have been reprocessed and labeled in a standardized fashion, allowing anyone to reanalyze that data using specialized resources or generic resources, but there are comprehensive analysis tools that we'll talk about a little later. Okay, so when considering an RNA-seq cure of this nature, it's important to think about what kind of research questions can students use the public RNA-seq data for. And so some questions are the findings from a scientific paper reproducible? Can I discover new relationships from the data? How does the choice of controls affect the results in related papers? And to what extent are negative differential expression results explained by low sample size or read counts? Okay, so many different kinds of learning objectives are possible with this kind of cure, including students achieving a deep understanding of related genomics concepts related to data and data sources, methods such as differential gene expression, Go analysis, that is gene ontology analysis, designing a research question, and experimental design in general. Students can gain information and technological literacy regarding emerging tools used in genetic analysis. They can practice analytical and creative thinking, critical questioning, and examination of evidence. All right, so what kind of background information is needed for students to prepare for a cure? Well, they're going to need to understand the biological setting. So, what makes the disease state, how is it defined? What makes a cancer cell a cancer cell? What is a transcriptome? Regarding the methodological approach, what is next generation sequencing or differential gene expression or power? And so we've been collecting resources that'll help people to address these kind of broader questions. And I want to know what people think would be useful for us to generate here. All right, so what kind of work would students do for a cure involving reanalysis of data sets? So they would first need to read the paper from which the data originates. And the data would be coming from, we're promoting the GRAIN website, although none of us have used it for a cure. It seems like it's a very promising data set and approach. Okay, so what would students do? They would reanalyze quality control measures of the data, visualize expression patterns among samples in the whole data set, perform differential expression analysis and sample size and power analysis for the purpose of informing experimental design of future studies and understanding extent of false negatives. Okay, they can also do gene ontology and network analyses. Students are assessed through various pedagogical strategies to gauge their progress on learning gains. And due to time and space constraints, I can't run through an entire example, but this example is taken from Al-Mahi et al. 2019, which explains the grain resource, that tool. And here I just emphasize a few analyses from the GRAIN tool. So this is, GRAIN stands for GeoRNA-seq Experiments Interactive Navigator, and is a comprehensive RNA-seq tool. It's web-based, it's a platform with integrated data and tools. And here, Almahi reanalyzes a geo cancer data set. On the top graph, we see an overall view of similarities among samples in a PCA-like plot of overall similarity in expression levels among samples. And it's kind of small here, but samples are shown to first split that by triangle versus circle, which is a reflection of malignant or non-malignant cell type. And then between RNA fraction. So first it's kind of a left to right, and then a top to bottom flip or division in the data, showing that the major source of variation among samples is among malignant and non-malignant cell lines for breast cancer. On the bottom, we see a power analysis plot from GRAIN, and they call it a gene detectability plot, which I thought was really interesting. On the bottom of the plot is expression level, so average log 2 counts per million. And variation is on the y-axis, so biological coefficient of variation for each gene. And so genes with higher effect sizes or fold changes are shown as solid triangles. And 3 types of genes are described on the left. In red are genes that were not differentially expressed, but were not detectable due to low read count and insufficient power. In green are differentially expressed genes, DE genes, and in black are genes that were not differentially expressed, but were detectable. And so they kind of represent true negatives. They were sufficiently expressed, but not different. So again, represent true negatives. So these are some of the tools that the GRAIN can produce. Again, gene ontology and network analyses are also possible. So I think that this is a promising approach. Again, none of us have tried it, but maybe this fall I will try it in my genetics class. Okay. So we wanted some help thinking of different ways to use existing data to sponsor cures. So if you have any ideas of existing data sets and how students could use them to to generate cures, that would be great. We'd love your feedback and love to hear your ideas for examples that kind of pave the way for others. And these are great because they're free and easily accessible. As far as all you need is a computer and an internet connection. Next week, some of the discussion questions that we're going to be considering in the synchronous session would be what materials would be most helpful for us to generate at the Genomics Education Alliance? What are viable options, do you think, for first year students? What kind of analyses and, and research questions? How else can we help students develop a good biological research question given the tools that are available for RNA-seq analysis? And what resources are needed to make these tools more teachable? So those are some of the questions, and we'll see where the discussion leads us. I just also again wanted to mention that Sally Elgin and Wilson Lung have created a template for cures involving eukaryotic gene annotation, and their work is linked to this, and they will be similarly looking for feedback so we can also discuss their template next week. Thank you.